Now we are going to end the result. Let x and y are normed spaces. F from x to y be linear. If f is continuous, then and of finite rank, f is continuous and of finite rank, then f is a compact. F is a compact. And range of f is closed in. Y. And range of f is closed in Y. Conversely, if x and y are Banach spaces, x and y are Banach spaces. Previous case only y is Banach. Here x and y are Banach spaces. F is a compact map. If x and y are Banach spaces, f is a compact map. F is compact. See, f is a compact map, and range of f is closed in Y is also called. Then f is continuous. F is continuous and of finite rank. So this is our next result. X and y are normed spaces. F from x to y be linear. The necessary part, if f is continuous, continuity of f is preserved and of finite rank. So consider f, let f is in VLXY. F is linear, which is continuous, then f is a bounded linear map from x to y. Okay, f is in VLXY. Let f is in VLXY and of finite rank. And what about the range of f? Range of f is closed in Y. Since range of f is of finite rank, then range of f is finite dimensional and it is closed the subspace of Y. Closed in Y. Then when x is a norm, we know that when x be a normed space, Y be a subspace of x. This is a result. X be a normed space, Y be a subspace of x. If this Y is finite dimensional, then we know that this Y is complete and is closed in x. This is an important result. When x be a normed space, Y be a subspace of x. Then if Y is finite dimensional, then Y is complete and closed in x. So here f is in VLXY and of finite rank. Here range of f is finite dimensional and also closed in Y. Then we know that f of u closure is a bounded subset of Y. Clearly, f of u closure is a bounded subset of Y. Okay. Let x fall in f of u closure means there exists some xn fall in u such that x equals limit of f of xn. That is let x fall in f of u closure. That means there exists some xn fall in u such that x equals limit f of x. That's the convergence. So what is norm x? Norm x equals, or norm x less than or equals limit of norm f of x. Okay, that is less than or equals to norm f into limit norm f into norm x. Xn fall in u, norm xn strictly less than 1. So clearly this x is bounded. means norm x less than some alpha. Norm x less than some alpha. That implies f of u closure is bounded subset of y. Why? Because x less than, so x fall in f of u closure. Agree? So f of u closure is a bounded subset of y. Clear? F of u closure is a bounded subset of y. Then clearly f of u closure is a closed unbounded subset of y. Hence it is compact. F of u closure is compact. F of u closure is compact means f is a compact linear map. Okay. So this is the necessary application. Come to its reverse inversion. Reversing, let x and y are Banach. X and y are Banach spaces. X and y are Banach spaces, and what is f? X and y are Banach spaces. A range of f is a, that is the theorem states that if x and y are Banach spaces, f is a compact map also. F is a compact map. F is compact. F is compact means f of u closure is a compact subset of y. Then such that a range of f is closed in y. Then to show that f is continuous and of finite map. That's our requirement. A range of f is closed in y. Range of f is closed in y. Also f is compact. We know that f is compact means f of u closure is a compact subset of y. Compactness implies continuity, hence f is compact means f is continuous. Continuity of f is finished. Okay. Right. When y is Banach and f is compact, then a range of f is also a Banach space. Range of f is a Banach space. Okay. F is from x to y is a Banach space, so range of f is also a Banach. And f from x to this range of f is onto, which is surjective. Let's image. Then by open mapping theorem, there exists an open ball u in x such that f of u is solved. Okay, there exists an f from x to range of f is a surjective map. Then by open mapping theorem, there exists an open ball u in x with f of u is open. Now, f of u is open. Now, let delta is positive. Consider, let delta greater than 0. Now we define a set, let E equals set of all y fall in a range of f with norm y strictly less than delta. Norm y strictly less than. You can define a set E, set of all y fall in range of f such that norm y less than delta. So clearly f of u is open, then this E is a part of f of u. E is an open set. Why? Because of this definition, norm y strictly less than delta. This is an open ball having radius delta. Then clearly this E is a part of f of u. Okay. Right. Now, so consider this set of all y fall in range of f with a norm y less than or equals delta. Surely it is a part of f of u closed. Less than or equals delta. Closed unit. It's a part of f of u closure. But f of u closure is a subset of y. Why? Because f is a compact map. Then f of u closure is a compact subset of y. So f of u closure is a compact subset of y. So here f of u closure is a subset of range of f. Why? Because range of f is closed in y. Okay. So this f of u closure is a part of range of f. But it is given f of u closure is a compact subset of y, which is compact. Then the closed ball of a radius delta in the normed space, a range of f is compact. So the closed ball having radius delta in the normed space range of f is compact. That means range of f is finite dimension. Why? Because we have a theorem that is if x be a normed space, then the subset, we have a theorem, if x be a normed space and the set of E equals set of all x foreign x with a norm x less than or equals 1 is compact, then x is finite dimension. This is a well-known result in function analysis. So, with the light of that argument, we know that there is a unit ball having a radius, the closed unit ball having radius delta in the normed space range of f. So, in the light of this argument, we can say that range of f is finite dimension. The continuity of f is immediately preserved. Why? Because the compactness of f. And for the finite dimension of this f, range of it is we define as it E. That's an open ball. Surely it is a part of f of u. Let y fall in E. Norm y less than delta. Then this f of u is an open ball. Then norm y less than or equals delta is a part of f of u closure. But surely since it is compact, it is a part of range of f. That means the unit ball having closed unit ball having radius delta, which is in the normed space range of f. So surely, according to this result, this range of f is finite dimension. That is what we require. Okay, thank you.